Hello students, welcome back to the next lecture on classical electrodynamics, and today we have lecture number 5. In the last class we have seen the general discussion on the solution to the Poisson equation in electrostatics, and remember that the Poisson equation is an inhomogeneous differential equation, which means that the right hand side of that equation is not equal to 0. In case for some reason the source term is 0, okay, that means the right hand side is 0. In case if that happens, then you will be having the del square of the potential will be equal to 0. That is, right hand side you are going to put 0. When that happens, we will rename the Poisson equation as the Laplace equation. So basically Laplace equation and Poisson equation are closely related, and the only difference being that the right hand side will be not 0 for Poisson and it will be equal to 0 for the case of Laplace equation. So therefore, you already know that the green function method that we have discussed in the last class is going to be useful only for the inhomogeneous differential equation. And in addition, if the charges are present, for example, then the Dirac delta function has to come into picture. You already know, of course, we have seen what is the reason. That means whenever the charge is present, we say that the value of the charge is spiking to some number, and then suddenly in the neighborhood you don't have any charge. If you have one charge in one particular location, then the charge is present over that region only, whatever small region that you have. Okay, whether you are going to say there whether it is 10 to the power minus 15 meter, whether it is that kind of number or not, we do not have an exact number for the diameter of the electron. Okay, if you are going to consider that an electron is going to be a charge, we don't know the exact diameter of an electron. Okay, if you are going to estimate something like 10 to the power of minus 15 meter, certainly it's going to be smaller than that. Okay, only for that small region you have the charge, and if you come outside that region, electron itself is not there. If at all it is there, it should be another electron. So you understand the purpose of the Dirac delta function. Okay, the Dirac delta function should peak. Peak means the value of the electronic charge. The value of the electronic charge is the peaking value. And then once you come out of that 10 to the power minus 15 region diameter, then you don't have the charge. That means 0. So this is the practical situation where the Dirac delta function is going to be useful. And whenever the charges are present, then the corresponding equation will be the Poisson equation. And the solution to the Poisson equation is generally treated in terms of Green's function. And the Green function itself can be determined by imposing the Dirac delta function as the right hand side. So the entire story we have seen in the last class. So now the point is the following. Suppose if I have Laplace equation, that means the right hand side of the Poisson equation is 0, then we don't require a Green function, because it is not at all a inhomogeneous differential equation. That is first point. And second point is that in the absence of the charges, that means I don't have the charge at all. There are no electrical charges. That means the right hand side is the, right hand side of the Poisson equation is what? Electronic charge density divided by epsilon 0. So if that quantity is 0, that means you don't have any charge there. If that is the situation, I don't require Dirac delta function also. So we are in a much better situation, because we don't want Dirac delta function. At the same time, we also don't want Green function. So we are interested therefore to the solution methodology of such an equation, namely the solution to the Laplace equation. And as usual, we will be dealing with the three-dimensional situation, particularly in polar coordinates. Maybe we will start with the spherical polar coordinate. So once we discuss the solution in the three-dimensional polar coordinate, for example, then it would be quite easy for you to learn how to do the calculation in the Cartesian coordinate system. Okay, Cartesian also three-dimensional, but we are not going to explicitly write down the equation for Cartesian, because that would be quite simple after finishing the calculation in both the spherical polar coordinate system and in the cylindrical polar. Okay, so the point is now clear. What is the today's work? Today we are interested and asking or interested to solve, for example, the Laplace equation in three-dimensional spherical polar coordinate system. If that is the situation, a certain thing is clear that we are not at all interested in the requirement of the Dirac delta function, and also we don't want the green function. So we have a solution methodology without these things, and the solution methodology is going to be quite simple. But however, I'd like to tell you that there are certain requirements. Okay, that means if you already know certain things, then it would be quite comfortable to proceed the solution methodology without making any digression. That means without deviating from this original topic, we can continue. So let us therefore see what are the basic requirements, or what we call some kind of a background mathematical knowledge which is required, so that using that we can quickly learn the solution methodology. So in general, whatever I am going to refresh your memory in terms of certain graphs now, or in terms of expression, should be quite comfortable to you. They are not new, by the way, because you already studied the mathematical physics first course in your first semester. So there is nothing difficult, but however, we need a particular differential equation and how the solution is going to be looking like. That is first thing. Second thing is you have to pay attention to some minute details in the differential equation. Okay, so those points I would like to emphasize, so that we will not be deviating from the main discussion of the solution methodology. So at the time of explaining the solution methodology, I will not deviate the topic and then explain these kinds of minute details. So for that purpose, right now we will see, I would like to show the plotting of a particular function, and then see what is the observation that we can gain from that. That is one thing. And then I would like to explain what is the solution to a certain differential equation, and some particular points about the differential equation, namely the singular points. Okay, some points are there where the solution doesn't exist. Okay, so those points will have to pay little attention, and once the things are clear, and if you assemble this information and keep it with you, then it is quite simple that we can proceed to the solution of the Laplace equation in the three-dimensional spherical polar system. Usually in the textbooks they write the entire thing in a one stretch, so it appears as if it is a very lengthy discussion. So it is not so. If you learn bit by bit and keep separately, that means the mathematical background that you have, then writing down the solution is only a matter of a few steps. Okay, even though it is spherical polar coordinate system, solution is going to be fairly simple. That's what we are going to see. So this is going to lay the foundation. That means that today's class work is going to lay the foundation towards learning the solution to the Laplace equation in spherical polar coordinate system. So let me go to the screen, and then I would like to show the plotting of a particular function, and followed by the explanation. So let us go back to the screen now. So here is the graph. I am interested to plot the sin x graph. Of course, you can see, I think it is going, let me go back here, which I am plotting right now. Okay, so what I am trying to plot is, I would like to plot the graph for sin x, which is quite simple thing. That is why I have started with this. And sin x means sine of 1 into x. So naturally the question comes, there is a 1 there, and therefore I would like to change that number 1 to any other number. Suppose if I change it to 1.1, 1.2, etc., how this particular graph is going to look like. So that is what I would like to explain, and there is a point to be noted after finishing this graph. So the point, or what is the place, or in which place you have to focus the attention, is the ability to repeat itself. We say it is periodic function, right? Periodic function means ability to repeat itself. What is repeating, you see? So this is a 0 here. It is going to some kind of a maxima, and then coming to again 0. So this is also 0, this is also 0. So the question is that after this 0 value, what is 0 value here? Y-axis. I am talking about the y-axis 0. Okay, it goes to a maximum. That means the y-axis is 1, and then it comes down to 0. So that 0 is here. So this is 180 degree. Okay, 180 degree is x-axis, 0 is this side. So now the question is, because we got the y-axis as 0 once again, now we are asking the question whether the same thing is repeating. Same thing is repeating means maximum and then come to minimum. So So will I get a maximum and a minimum like this? That's what we are seeing, but it did not happen. It is going to negative in this direction and then going up here. And therefore, we say that this particular function is not periodic at 180 degree. This point is clear. This particular graph that is shown here in the red color is corresponding to the sine of 1x. That means sin x. You are asking the question whether the sin x is periodic at between 0 and 180. So the answer is no, because after 180 degree, this particular function is not repeating, but instead you still get a different type of graph. So it goes and it keeps going until 360 degree. This is 360 degree. So after 360 degree, if you see the behavior, it is now increasing. So that increasing part is, and this increasing part is going to be identically same. And now we would like to make a conclusion that the function sin x is going to be periodic between 0 and 2 pi. So 2 pi is radian, 360 is degrees. So this point is clear, right? So we are now asking the question when the particular function will be periodic, or we are asking the question between what angles. You have to tell between this particular region to that particular value of the degree or angle. You have to decide, or you have to make a conclusion that the function is periodic or not. So for sin x, it is very clear. For sin x, the periodicity is 0 to 2 pi. After 2 pi, what will happen means whatever is happening at 0, the same thing will repeat. That is what is going to happen. Now, if this is clear to you, I would like to change the value of m to some other number. So let me therefore change and then show what is happening there. Let us change it to some number like 1.1. This is 1.1. That is 1.2. Okay. So now what happened is 1.2 is the red color graph. The red color graph is corresponding to sine of 1.2 means what? Sine of 1.2x. Okay, that is the function. And as usual, the theta or the x-axis is this numbers 0 to 360. Now you please again focus your attention. Forget the green color one. The green color one is the sine theta graph. For reference, I am keeping. That was the graph that we started with. So for reference, the green color graph will be in the background. So now because of the 1.2, what happened is the graph has become the new graph. Now you see that it is now, you see the maxima is there, the minima is there. Now it is coming to 300. This is 360. Okay. So at 300 degree itself, it is becoming 0. And afterwards, you see the increase. So that means now you tell when this particular function is periodic means now it is not 0 to 2 pi. What is your answer? The answer is 0 to 300 degree. You can convert 300 degree to radian. Okay, that is fine. But now let me tell in terms of degree. So now in the earlier case where m was equal to 1, that is a green color curve, the periodicity is 0 to 360 degree. That is the answer. When you change m equal to 1.2, now the periodicity is between 0 to 300, not 360. So this is the point to be noted. Okay, then what happens? Let us see. Let us increase this number to some other value. So let me increase to some other value. 1.6. Now 1.6, what can you say? As you see that for 1.6, you can see that there is a red color graph is peaking like this and going to 0, again going in the downward direction, coming back to original 0. Okay, that is the same 0 as like this. Then what happens is this is repeating. So after this portion, this particular red color graph is repeating. So now this is the number you have to carefully see. This is 240. This number is 240. So what is this? You can see. So certainly earlier it was 300. Okay, you started with 360 for green color graph. Then it came to 300 periodicity. Now the periodicity has come to even below 240 degree. So now the point is therefore clear that if you keep on changing this m value, the periodicity of the sine function is also changing. Only for sine theta it is 0 to 2 pi. Okay, you should not assume or you should not think that all the kind of sine theta like sine of 1.6 theta, sine of 1.2 theta, everything will not have the 0 to 2 pi periodicity. This is the conclusion. Okay, so in order to demonstrate this graph is going to be very useful. Then the question comes, next question comes. Okay, 1.6 is there. Why don't you try 1.7, 1.8, 1.9? If I increase that, anything is going to special or it will be behaving this way? That is a question that is naturally arising. And therefore, let me increase this number little bit. 1.8, okay, still it is similar behavior is there. 1.9, 2. Now 2 something happened special here. Now that's why I'm stopping here. 2, what happened, you see that the red color graph is there here. So the red color graph that you are going to have like this is going to be periodic like this. So up to this you consider. So now what happens is at 360 degree it is matching with the green color one. That is the point to be noted. And the second thing is after 360 degree the red color graph will repeat itself. And what do you mean by m equal to 2 is sine 2 theta. Sine theta is the green color graph. Sine of 2 theta is the red color graph. So now, so what is the point to be noted is that sine of 1 theta, after that now sine of 2 theta. This 1 and 2 are integer numbers. But when we are trying to put the numbers like 1.1, 1.2, which are not at all integers, then the periodicity was not 360 degree. And therefore, let us therefore make a conclusion. The conclusion is that provided that, or if and only if there is a integral multiple, okay, of theta, integral multiple means 1, 2, 3, etc. Okay, those numbers only are allowed. Fractional numbers are not allowed. When integral multiples of theta is there for the sine function, only in that situation the function will be periodic between 0 and 2 pi. So we are now recovering back the 0 to 2 pi condition, isn't it? For 2, for 1.8, for 1.9 there is no chance for 360 degree. Okay, it is some other number was there. So the set of all functions, okay, that's what, let me probably I will write down once this is over. I will go to the, so if I go to the board I can see. So now you can see that if I am moving from 360, 420, etc. Now you see that once again the same red color is repeating up to 360 plus 360 is 720. Isn't it? That's what I have moved the graph and showing. That is what we say it is repeating. So the periodicity is there now. So this particular information I would like to write down. In the board. So let me therefore go to the board now. Yes. So now as you can see that I'm just labeling whatever I have explained to you. So this red color one could take any number, but we are interested in only in the integer values because we are able to gain the periodicity 0 to 2 pi. So any other number that is this kind of 1.6 which is not at all an integer will not be periodic over 0 to 2 pi, and therefore we are not interested. So we need a periodic function between the limits 0 to 2 pi. So that is the reason why we have been discussing this particular topic. But then the point to be noted, you can ask the question, what is special about 0 to 2 pi? Why do you want to demand this kind of condition 0 to 2 pi? Is because we are interested in solution to some differential equation in the spherical polar coordinate system. So spherical polar means, you know, right? R comma theta comma phi. Radius r means what? What is radius? So 0 to infinity. Any radius is possible. Theta is the polar axis. What is the allowed value for the theta is only 0 to pi. Okay, according to the spherical polar coordinate system, allowed range for theta is only 0 to pi. But what about phi? There is another angle, no? R theta phi, the last variable phi. For that, what is allowed value? That is azimuthal angle. The allowed range is 0 to 360 degree. Okay, the theta, that is a polar angle, means 0 to 180 degree. Azimuthal angle, so that is what we are interested in. Azimuthal angle means the angle that is measured on the horizontal plane, that is called azimuthal angle. If you are going to measure the angle in the vertical plane, then that is called a polar axis. So for the azimuthal angle, the allowed range is 0 to 2 pi. That means on the sphere, if you travel 0 to 2 pi, then we will come back to the original place. Our starting place, we will come back in the horizontal circle. That's the meaning. The vertical region, we are not going to do that. Okay, in the vertical region, only 0 to pi is there. Of course, I don't want to explain now why it is so. The explanation is there in my other lecture under the name of spherical polar coordinate system. There's a separate lecture on that. So there you can find the explanation why 0 to 180 degrees is there for polar angle. Okay, so now it is clear why we are interested in the region 0 to 2 pi and then making this kind of a conclusion. That means we want to reject this kind of condition. So the clarity is therefore clear. This is related to the spherical polar coordinate system azimuthal angle. That is why 2 pi is we are interested in. Okay, so once these things are clear, I would like to therefore write down. I want to write down that this is the conclusion. Probably you can see that. So the conclusion is therefore clear. Whether you take sin mx or whether you take cos mx, sin is the one which we have plotted. You can also plot cos, but the consequence and the conclusion is same. We have the periodic function over the region 0 to 2 pi if and only if the variable m or the parameter m is belonging to the set of all integers. So set of all integer is this. It should belong to that integer set only. Okay, not any fractional value. And the idea about the axis why you have chosen is because the connectivity is there with the azimuthal angle in the spherical polar coordinate system. So usually whether you call it as a sine theta or a sine phi, okay, sine theta is a general way of writing down, but since it is a spherical polar coordinate system, we are talking about this particular phi, and therefore we are interested in the region 0 to 2 pi. Now whether you plot it sine theta or whether you are going to plot cos theta, whatever it is, okay, where we can replace theta by phi, that combination, that is called linear combination, right? Some kind of cos theta plus some other number into sine theta. You remember what it is? Cos theta plus I sine theta. That is a linear combination. Okay, sine cos theta plus I sine theta is the e to the power of I theta. So that is what I am writing here, that any kind of linear combination of the sine and the cos can be written down as e to the power of I theta, the familiar Euler formula that you know, right? That is exactly what I am writing, right? And the mx is theta means here also you can write mx, but since x is theta, we are now writing e to the power of I m phi. So our conclusion is therefore very important, that a linear combination of the graphs of sine theta and cos theta can be written in a compact manner, that is called the linear combination, can be written down in a compact manner like e to the power of I m phi. And the demanding condition is the conclusion, very important conclusion, that m cannot take any number, but instead it has to be an integer. A negative integer is okay, positive integer is okay, 0 is okay, all these things are okay, but only fractional values are not acceptable. So this is a very important conclusion. We are going to use this particular expression when we are trying to solve the Laplace equation. So at that time, I don't want to deviate to the track and then explain this particular point. So remember this point now. Whenever we need some kind of linear combination of sine theta and cos theta, then it is called e to the power I theta. The only thing is that this multiple has to be an integer only. So keep that particular point. And there is another interesting point I would like to mention here, that the same result is going to be extremely useful in quantum mechanics. Same result. In quantum mechanics, once again, you are going to study a very similar situation of the del square operator in quantum mechanics. Del square operator is what? Laplacian operator, right? In your Schrodinger equation, you have minus h cross square by 2m into del square. That is the del square, same del square only in electrostatics also. So del square will not change from subject to subject. And therefore, if you are interested to solve the Schrodinger's equation in the spherical polar coordinate system, same story will once again come. And therefore, this particular conclusion has to be remembered in, and m has to be an integer here. So now you understand what is this integer. This is the important point. In the language of quantum mechanics, we say that this particular thing is quantized. We say quantization, right? Quantization of angular momentum. That is what is this actually. Now what is that quantized means? In mathematics we don't use the word quantization, we use the word integer. In mathematics, what is known as integer is exactly what is quantum in physics. Quantum means integer. That means there is a number 1 and after that only number 2 will come. 1.1, 1.2 will not come. That is an integer. So there is nothing new. In mathematics, this is a well-known fact, right from the school you start learning for the integers 1, 2, 3. At that time you never ask in between 1 and 2 what was there. So the story about the integer is quite fundamental in mathematics, and therefore there is no surprise for mathematicians. But for physicists, when you're talking about the angular momentum, when you solve the same equation, when this m is going to be integer, what happens is that this particular quantity is going to represent angular momentum in quantum mechanics, for example. Then we say that the angular momentum in the z direction is quantized. So angular momentum is quantized means it is direct consequence of this particular expression. Basically, it is the we are talking about the periodic solution over the region 0 to 2 pi. That's what it is. If you are demanding periodic solution, then m has to be an integer, and we say that corresponding physical quantity representing the del square operator in the 3 dimension happens to be an angular momentum operator in quantum mechanics. So the story is the same thing. So that's the point to be noted. So whenever you are going to demand an integer condition, we say that that particular quantity is quantized. The same thing is true in the case of the particle in a box, because you are quite familiar. And you ask the question why in a particle in a box why n was one, why n has to be an integer. When you write sine of n, you traditionally write sine of n pi x by L. Now, why n should be an integer? From where that condition came? So the condition has come from the boundary condition. Okay, it is the boundary condition to the differential equation. That is the point. There is no physics there. Boundary condition is a mathematical imposition. You are imposing mathematically that certain number should be fixed at the boundary. Consequent upon that, you have a demanding condition that this kind of m or n, whatever it is, should take only integer. So therefore, quantum nature that you are observing in the quantum physics is direct consequence of the boundary conditions in differential equation. So it is a direct consequence of differential equation actually. Okay, especially applied boundary condition. If you don't apply any boundary condition, then there is no particular solution, so you can't discuss anything. So that those things are clear. So now I would like to emphasize that this kind of situation is quite common in whichever area you are going. As long as you are going to discuss with the spherical polar coordinate system, this kind of story will enter into picture. Okay. So this is first point. I would like to say that this is the first point, or I will say, okay, whether it is a result or whatever it is, I would like to now say that this is one of the important results that is required. Now, once this is clear, I would like to move on to another important discussion which is required. Let me therefore write down a differential equation. So let me call this particular one as the first result. And because we would like to discuss another two more results, for example, so let me therefore write down that I would like to discuss on some result from the differential equation. So I will write it as another topic. Okay, let us say second topic, and the result that we are going to get it is a result 2. Just for remembering, we are giving the name, and the differential equation that I would like to pay attention right now is what is known as the Cauchy Euler differential equation. These things are quite familiar to you, but let me therefore explain. X square into y double prime plus 2x times y single prime minus some constant into y equal to 0. So this any differential equation that is looking in this particular form is known as Euler differential equation. And of course, these are the standard notations, namely you should know what is an independent variable, namely the x is the independent variable, y is the dependent variable, and k square is going to be a positive constant. And of course, it's going to be integer. We are going to put the condition. So let me therefore explain this clearly. Why we have, of course, minus or plus, that is not a problem here, whether it is plus k square or minus k square. In all the cases, it is known as the Cauchy Euler differential equation. So that is not a problem. You can have a plus also. But we are now interested for our problem on the solution in the spherical polar coordinate system. For the Laplace equation, minus is going to come. So that is why let us have this kind of an equation. And as you can see that this equation is a linear differential equation, so second order differential equation, variable coefficient, because x square, 2x, these things are variable coefficient. Only k square is a constant coefficient. So therefore, the traditional techniques that you already know for the auxiliary method equation, whatever you call, those methods will not work when you have variable coefficients like this. And Cauchy, by the way, Cauchy Euler differential equation belongs to a much wider class of problem. Okay, so it doesn't stay only with the x square. You can have many more terms here, but whenever the appearance, we are not going to discuss much broader topic of what is the set of all Cauchy Euler differential equation. Okay, that right now let us not discuss, but among that, one particular equation is going to be very useful for us right now, and that equation is only particularly second order. Okay, higher order is also available for Cauchy equation. So this is the thing, and what is the point to be noted in the Cauchy Euler equation is that if there is a second order differential, that is d square y by dx square, if there is a second derivative, the power of x is 2. If this is first derivative, so power of x is 1, x to the power 1, right? And what is y? Y means zeroth derivative of y. Y means what? Y means it is not at all differentiated. It is the original y. We say it is zeroth derivative. If it is zeroth derivative, what should be the power of x? Here the power of x is 0. So what is x to the power 0? Power of x 0 means x power 0. X power 0 means 1. So there is a 1 into, you have a k square into y. So this is the general form of the Cauchy equation, and if you are going to add additional terms in the left side, plus if you want to add plus y triple prime, for example, then the power should be x to the power 3. Like that, many terms can be added. So the differential equation order and then the power of the x will be same in all the terms that you can add. So that is the condition that is required, one of the condition. And coming to this particular point, when you say constant, why do you want to put k square? You can put some c. C is a constant, right? So why don't you say that c into y equal to 0? So this is the point to be noted, that when you write a square, it means that it has to be a positive number, because it is already square of something, right? Even if you take a negative number, if you square it, it must be a positive number. So by writing a k square here, you are indirectly providing the clue that the k square has to be a positive number. This minus is a different story. K square itself is a positive number only. You cannot have a k square as a negative number. In case if you want to agree for negative number, then you are going for a complex variable. Okay, so right now this differential equation is a real variable differential equation, in which case k square has to be positive. Positive number is okay, but there is a restriction going on here, and we are going to discuss a special situation where any number is not there, only integers are acceptable for some reason. Of course, we have seen just now one reason in terms of a graph. Somehow these things are going to be connected. You've seen the graph for sine theta and then sine of 2 theta. Sine theta and sine 2 theta is going to be periodic over 0 to 2 pi, and for that reason we accept only integer values. Like that one condition, it is not the same condition. Like that, another condition is going to come, which is going to put the restriction on the what kind of number can be k square, and we are going to see later that only integer values are acceptable for that reason, some reason. Okay, not the graph reason. The graph that you have seen is another reason, which is let us see that later. So a similar reason is going to do this kind of tricky behavior, that only the integer values are acceptable, for this particular differential equation. And remember, for the Cauchy Euler equation, you can have any number. Any real number is acceptable for the Cauchy Euler differential equation, but for our physical problem of solving the Laplace equation in the spherical polar coordinate system, we are going to see later that only integer numbers are acceptable for physical reasons. Okay, so this is the basic information, and therefore once you know this, the solution methodology is quite simple. It's not complicated. So let me therefore quickly write down how you can do this, and I will say what is the method to be done. Okay, it is a linear differential equation with variable coefficients, so that much you keep informed, and then we can proceed further. So what is the method that you can use? You have two ways of solving it. One is to use transformation of the independent variable. Okay, I will not explain this kind of terminology, but you understand that transformation of independent variable can be done. That is one option. The second option is that you can use the simple substitution. Substitution in our problem could be y equal to x to the power of some number lambda. Okay, so that is the idea. Both of them will work actually for this problem, and usually the transformation method is useful when the equation is inhomogeneous. That means right hand side is not equal to 0. But in our problem, you already know that right hand side is 0. Therefore, the substitution method is going to be useful for us. Both the methods will work. Okay, so the point is now clear, right? Because the right hand side is 0 in this particular situation, both method will work. Even if right hand side is equal to 0 also, this particular transformation method will work. But the method of transformation of the independent variable will take a little more work. You may have to work for one sheet of paper or two sheet of paper, only then you get an answer. But substitution is not that lengthy. Okay, a little bit you can quickly get the answer. Okay, that means less number of steps you will get the answer. So therefore, even though both the methods are going to be successful method in solving this particular differential equation, we will choose now the substitution method because in less number of steps we will get the answer. So therefore, let me put let us choose this particular one. That is what I am now putting a circle, and let us proceed now in this particular direction. So if we are going to keep, okay, we are going to make a substitution that y equal to x to the power lambda, then what will happen if you differentiate? So then y prime would be equal to lambda into x to the power of lambda minus 1, and similarly you can do the second derivative. It's quite simple. So that's all about it. You have the two derivatives and then substitute these things into the given differential equation. Okay, substitute all these things into given differential equation, then you will get the answer quickly. Let us see the steps now. So let us substitute. So the differential equation becomes x square into you have a lambda times lambda minus 1 into x to the power of lambda minus 2, then plus 2x times, that is 2x, okay, 2x times, then you have a lambda times x to the power of lambda minus 1 minus, then k square x to the power lambda equal to 0. And that's all. So the rest of the thing is quite simple. Let us see. We can take something common and then write down, so no explanation. Let me take something common and then write down. Okay, so you have a product of the two things, so which means that either you can have an x to the power lambda 0, or you can have the quantity inside the bracket to be is equal to 0, or another situation is both of them are equal to 0. So these are the only possibilities that you have. We have to be careful. Okay, it is not that something it is too simple to be taken for granted. So if you are going to consider x power lambda 0, what is the consequence? Either you can consider x equal to 0, or that the power lambda can be minus infinity. Okay, but what do you mean by x equal to 0 is a trivial solution. Isn't it? Trivial solution means what? Without doing anything, you can say 0 is the solution. No, that is called trivial solution. So we don't want that trivial solution. And therefore, we will consider the second option now. And in that particular second option, we will solve this by a simple quadratic equation. So minus b plus or minus that formula, you use it. And let me put them the corresponding values. Minus k square, you note down. Okay, it is not plus. Okay. So there you have to be careful, and okay, divided by 2 into a equal to 1. So we have the lambda equal to plus minus, you have 1 by 2. Then the square root, what happens is we are unable to write it as a square. So it looks like 1 plus 4k square. No, you can't finish. So this is a place, let me explain here. Now what is known to you is k square is an integer. Okay. So since k square is an integer, we can think about expressing this particular quantity in terms of another integer. Okay, let me finish this. In terms of another integer, what is the purpose of expressing in terms of another integer is that I want to write it as something to the power 2. I want to write it in such that 1 plus 4k square can be written down. Okay, this quantity can be written as something to the power 2. Why do you want to write something to the power 2? Did you understand? This is a quantity. Okay, now I am unable to remove the square root. Okay, if this entire thing is something to the power 2, then the square root and then the power 2 will cancel, and I can now simplify this expression. So that is what it is. Anyway, it is an integer. This is not going to be a fraction. So if there is a fraction, if there is something like 7.8, for example, total value, then square root of 7.8 will be another fraction. So that will be difficult. But what is our idea here? This is very important. What is the idea here is that this is an integer. K square is an integer, okay? Something like 10, 11, 12, whatever be the case, it's going to be an integer, and k square is positive. Now since this is positive, the entire square root is a positive only, so no question of complex value. Now there is a possibility, you have to think this, there is a possibility that what happens if there is a square root of 49 is there. If the entire expression is square root of 49, I can write it as 7, which means that this expression can be simplified conveniently. And 49 is an integer, right? And that is what I am telling. When k square is an integer, one integer can be written in terms of another integer such that it looks as a square of something. So that is the idea that we are going to get. If it is the case, how can we rewrite this k square? So like this, your mind has to work, okay? Based on that thinking, people have come up with an idea that, okay, k square can be written as square of another number. So that's what I'm writing. We can write it as k square can be written down as some other number square plus the same number. Okay, where L is a different integer now. L is different integer. Let us see what is the purpose. Now if you see, if you simplify within this one step, you can understand what is happening here. So you can take a 4 outside and then understand what is happening. You get an L square plus L. Plus L, let us write down L. Then you have an 1 by 4. So now what is happening is that now I am able to complete the square. That means I can say that 2 times L plus half whole square. Isn't it? So what is that quantity is 1 plus 4k square. So you should remember what is that quantity. Whatever we have written down is exactly nothing but 1 plus 4k square. So it's very clear that this particular case, this entire thing was k square, right? K square has been rewritten as L square plus L. What is an advantage is now the whole quantity 1 plus 4k square has been rewritten such that there is a power 2 coming. And if you are going to put a square root here, the square root will come here and then 2 can be cancelled, and L happens to be another integer. So this is how one can think about and then slightly modify the equation so that we can consider as an example how we can write like this is. If you want to see in terms of number, it is quite simple. Let us take something like, take some number like 7 into 8, for example. Let me write down an example. K square is an integer, that is clear. Let us consider that L is another integer. L is another positive, of course, naturally positive integer we are going to consider. Then in case if you are going to consider as an example 7, L equal to 7, what will happen? I will get 7 into 7 plus 1. How much is that? 7 into 8, 56. So let me therefore put the square root of 56 square. Isn't it? Since I am getting 56, this is how I can write. So what is the conclusion is that this particular number, that number, whatever I'm going to have, 56 is your k square. So k square is just 56. In that case, what is L? L is 7, isn't it? So L is 7, and therefore what happened is 56 has been rewritten as in terms of 7 now. So this is the basic idea of managing this situation. And if it is the case, let us go back to this, the quadratic expression. Then what happens? Let us simplify this quadratic formula. We have lambda equal to, we have this lambda is equal to minus half. Then I get a plus minus 1 by 2 into, so that entire expression is now, how much is that entire expression? You remember 2 times L plus half, right? So you write down that 2 times L plus half, you have to write down 2 times L plus half, and that's it. And now you can simplify. You apply the plus or minus is there, right? You apply a plus and then you apply a minus. So I'll get this after cancelling the 2, and this plus or minus you apply once, for plus you apply and minus you apply. Then we will be able to get the 2 values of the lambda. Let me therefore, I think I better write down separately. So let me explicitly write down, okay, both the values. For one side, let me write plus, other side I will take minus. So if I take minus common, I will get a minus of L plus 1. So our conclusion is that we got two values, lambda 1 equal to plus L and lambda 2 equal to minus of L plus 1. So this is the result that we have. So the advantage of rewriting in terms of L is clear, right? That we are able to simplify the quadratic equation. Okay, let us go back to this. So what happened finally? Did we get the answer? So our objective is that we are going to make a substitution. Okay, so that is what you have to remember. We are making the substitution y equal to x to the power lambda. So we where is y equal to x to the power lambda? Now put a circle there. So the same way, now the lambda is what we need. X power lambda means where is lambda? Now we got the lambda value, right? So use this particular lambda value in the equation y equal to x to the power lambda. And once this is done, you got the answer. So let me write down therefore the conclusion, since we are getting the answer now. Let me write down the conclusion that the solution to the given Cauchy Euler differential equation, CE I am writing for Cauchy Euler differential equation, is given by y equal to x to the power lambda, with lambda 1 being the L and lambda 2 being minus of L plus 1. Okay, take the linear combination. How do you write the linear combination? One solution is x to the power lambda 1. The second solution is x to the power lambda 2. Linear combination means put one constant alpha, put another constant beta, and then do the summation. That means addition. And that's it. This is the linear combination. Let us substitute that value. One is the another one is a minus, right? So I'll put a denominator L plus 1. And where alpha and beta are arbitrary constants, as usual for the case of linear combination. So now you understand how the solution is obtained. Now the point to be noted is that you don't have to repeat this every time. If you see the differential equation, you write down the solution. That is the purpose of making this kind of explanation right now. So you got the solution, and well, for which differential equation you got the solution? The Cauchy differential equation, right? So let me therefore write down so that you remember: x square y double prime plus 2x times y single prime, and then you get a minus of L into L plus 1. You now understand why this is written. Earlier we started with k square, and then now you understand that ultimately we end up with another number, positive number. Remember, L is a positive number, and we get this. So the purpose of doing this calculation is that whenever you get a differential equation looking like this, you don't struggle and then spend time in solution. That is not our job. The point I would like to explain is this one. If it is a mathematical physics paper, well, you can always explain what is the solution methodology. But we are not discussing mathematical physics paper right now. We are discussing electrodynamics. So whether you are going to write the answers for the electrodynamics paper or the quantum mechanics paper, whatever it is, you should not be explaining how the solution is obtained for a differential equation. That explanation is not our main objective. Our main objective is to explain our electrostatic potential. Okay, in this particular case, and in the case of the quantum mechanics, you will be discussing the angular momentum operator in spherical polar coordinate system. And there exactly the same equation will come there. So remember that. So what I'm trying to say is that whatever we have done in the last maybe some 20 minutes, that time you don't have to repeat in the case of answer papers of the quantum mechanics as well as in electrodynamics. But instead of that, what is required is you directly write like this. If this is the differential equation, you follow this. If this is the differential equation, then this is the solution, and that's it. That should be written. These two lines should be written clearly in the answer paper rather than explaining the steps for getting the answer. That is not required. That is what I am trying to say. Okay, if at all you want to explain everything like this, then it should be done in a mathematical physics paper. Okay, so let me therefore write down that this is the second result. So now you understand what I am trying to say. I don't want to divert the attention from the solution to the electrostatic potential. So directly we are going to write down that this is the answer. But you should remember how this has come, right? I am explaining this for the purpose of understanding. But in the answer paper, you don't have to explain how this has come, but instead you write down that for this particular differential equation, this is the general solution. And the important thing to be noted is L is a positive integer. Negative integers are not allowed. For example, if L is equal to -1, what will happen? If L is equal to -1, this fellow will become 0. Okay, so we don't consider that kind of a scenario there. Okay, L has to be a positive integer. Why it has to be a positive integer? You should remember we started with the k square. K square is already a positive number, so that positive number only we are rewriting. Therefore, this is compulsorily a positive number, integer only. So these are the underlying points that you remember, and keep this as a result 2. Okay, first result we have seen for sine theta graph. No, let us consider that this is your second result. And okay, let me keep this thing, and we will now discuss another differential equation, and then some important information about another differential equation is required. So let me go down here. I mean to say that we are going to discuss about another result. Now for that, how are we going to proceed to get another differential equation is like this. Consider the negative of the Cauchy-Euler equation. You know what is Cauchy-Euler equation? Okay, that is what is there right now. So if you are going to multiply the Cauchy-Euler equation by -1, simply multiply the equation by -1, then how the equation is going to look like? You get like this: minus x square. You just multiply by -1. Then you get a minus 2x into y single prime. Then I get a plus L into L plus 1 into y equal to 0. And that's it, isn't it? So you simply multiplied this equation by -1. So therefore we made a very small, we are going to do a very small change to this differential equation. Namely, I am going to put a 1 minus there. So the change I will put it in yellow color so you can observe it. I am going to put a 1 and that's it, over, and put a bracket. So that is the small modification I am going to do. You see what I am going to do? The small change I have written, right? What is the small change I have done? I have put a 1 here and then close the bracket here. That's what I have done. That is the only change that I have done, starting from the Cauchy-Euler differential equation. And that's all. This is another new differential equation that you are going to have. Remember, this particular new equation with this kind of a term here, 1 minus x square, is not the Cauchy-Euler equation. It is not at all Euler equation, because the structure has completely changed, and now that method will not work. The previous method will not work, and that this equation is another interesting, important equation, and you must be already knowing what is the name of the equation, and the name is the Legendre differential equation. So let me therefore write down that the name should be familiar to you from your first mathematical physics course. This differential equation is known as the Legendre differential equation. I'll write down LD. Now the point is here, it is clear. Now the value of the L in this particular equation. So you should remember that just because it is a Legendre differential equation, the value of L is a different L or same L. At that point I would like to clarify that it is the same number. That means same L that appears in the Cauchy equation. So same number will be there. So it is another equation with the same number. So that is a point to be noted. So, and now LD, what do you mean by LD? Legendre differential equation. So let us use it for convenience. And what is known to you, because I'm not going to explain the story of that, but it is already known to you. Let me emphasize some important points. This is a second order ordinary differential equation, and therefore how many solutions should be there? 2 linearly independent solutions must be there. It is there. Where it is there, you should know from your first mathematical physics paper. Okay, so these 2 linearly independent solutions are represented by PL of x and QL of x. So let me therefore make a point here. I am not going to explain how to obtain the PL of x. PL of x are known as Legendre polynomial of first kind. QL of x is known as Legendre polynomials of second kind. But there is a tricky point here. This point is important. PL is known as Legendre polynomial. QL is called Legendre function. This is not polynomial. So there is a distinction between polynomial, function, etc. So I'm not going to derive anything on how to obtain this starting from here. Actually, that has been done in your first mathematical physics course, and the methodology or what technique you are going to use the solution is the so-called power series solution. In particular, you can use either the Frobenius method or the power series method. Okay, because we are going to obtain the solution about x equal to 0, actually power series method will work. Okay, if you have singular points, you have to use the Frobenius method. Well, so that method we let us not go into the detail. Now the point to be noted is that we have two linearly independent solutions, PL of x and the QL of x. One is called the polynomial, that is called Legendre polynomial. The second linearly independent solution is not at all a polynomial, but instead is an infinite series. And we are going to call, or we say that mathematicians call that by the name function, Legendre function, not a polynomial. So therefore, this particular point should be important, and therefore I would like to make a note about this. Okay, this is important. So therefore, what is the comment that I would like to write down here is that what would be the general solution to the Legendre differential equation? That is the question, and the answer is this. So the general solution to the Legendre differential equation is nothing but linear combination of the two solutions. So that means A times the first solution plus B times the second solution. So this is the general story all the time, right? Whenever a sine theta and cos theta are two linearly independent solutions, what is the general solution? A times sine theta, B times cos theta. So whenever you get two linearly independent solution, this writing down like this is the traditional way of obtaining the general solution. But there is a now comes the important point. The point to be noted is that mathematically these things are fine. But when you are going to simplify with a particular number, because there is a number L, there is x number, x is the number, no? When you are taking numerical values, these things should not go to infinity. Mathematically, you can write all these things fine, infinite series. QL of x is an infinite series. When you have infinite number of terms are added up, there is no guarantee that it will converge, isn't it? So there is a problem of convergence, right? Sometimes it will converge, sometimes it will not converge. So now what happens is this QL of x has a property that it doesn't converge, especially at x equal to -1 and x equal to +1. So because of that reason, we have to be careful, and therefore let me write down this particular note here. So what is the note to be noted is that this QL of x, what is known as the second Legendre function, is an infinite series. That means it is not at all a polynomial. It's not at all a polynomial, and in particular, what is the trouble is, the particular trouble is that this particular infinite series does not converge, especially when x equal to +1, x equal to -1. See, it may converge somewhere else, but we are interested in x equal to ±1. So at those 2 points, it doesn't converge, so it goes to infinity, and therefore, when something is going to infinity, we don't want that, isn't it? Therefore, I will say that we will consider only the first term. You see the highlighting. So what I am trying to say is only this will be rejected. Rejected means we don't want. That's the meaning. Now the question is, how can you say that I don't want? So mathematically, how do you say is that we are going to put the value b equal to 0, or you demanded b equal to 0 for our solution, so that we can escape from infinity. So therefore, our conclusion, let me therefore write down that PL of x is basically a polynomial. Technically, it is a terminated series. Infinite series is there, it got terminated, and that is called a polynomial. Okay, originally it was a infinite series only, but it got terminated. That means numbers become 0. And whereas QL of x, that doesn't happen. And therefore, what happens is you demand that the constant that you are going to put is 0 there, so that this doesn't pose any problem of going to infinity. You know, infinity means the entire solution will go to infinity, right? We can't say electric potential is infinity. Okay, so this is all about the main important conclusion about the Legendre differential equation. So keep this as an important point, and what we will do is that let us modify this equation a little bit. Okay, you know that whenever you modify an equation little bit, we get another equation. So in that particular tradition, let us modify the Legendre differential equation. This is for reference, okay, because you already know we are going to modify a little bit. So keeping that equation we can modify. So I am just copying the same equation, minus 2x plus L into L plus 1 into y, that is equal to 0, where, and remember that in this particular equation, L is, what is the L? L must be belonging to the positive integers. So let me therefore put a positive integers represented by z plus. Okay, z plus is another option where this is technically called non-negative integer. So non-negative and positive are slightly small change. Non-negative means 0 also included. Positive means 0 is excluded. So that is the difference between non-negative and positive. Okay, so once these symbols are clear, what modification we want to do? So we are going to do a small modification, right? So let me therefore write down. We will modify the last term now. So let us modify. Modify means, adding some term, whatever you call, slight change. The change that is going to happen is only the last term. So first two terms, let me copy. And here is the change. Okay, let L into L plus 1, let it be there. I'm going to add one more term, minus m square divided by 1 minus x square. Okay, we have added one term. What is the term that we added is minus m square by 1 minus x square. The other things are same. Okay, L belongs to positive integer, m belongs to the set of all integer. Okay, so m belongs to set of all integer is important. Set of all integer. Okay, minus value is also allowed there. Okay, that's the meaning. Okay, this is the modification that that we are going to do. So what is this we are trying to do in this particular case is we can easily understand what is that additional term that we have added. What is that going to represent in spherical polar coordinate system? So that is what I would like to emphasize. So I would like to emphasize that this particular term that you added here is going to be connected to the spherical polar coordinate system. So I will write down that in the case of the spherical polar coordinate system, this equation is known as associated Legendre differential equation, ALD. I think better I will write down. Okay. In the case of the spherical system, what you have r comma theta comma phi, right? So the term that we added right now in that blue color highlighting is the one corresponding to the phi variable, and then the rest of all things, whatever you have, whatever other than that, whatever you have, that corresponds to the theta variable. Theta variable. So the next question therefore comes, what about r variable? Now r variable, what happened like that? You get a doubt, right? That is what we discussed already, namely the Cauchy Euler differential equation. These things are connected. Let us see how it is connected. Now you understand that Cauchy Euler equation, and then the theta part is known as Legendre differential equation, and then the last term what you added belongs to the phi means third variable. So they are all related, as you can see. So we are going to now ask the question, what is the connection between this third term? So the third term is actually going to represent azimuthal symmetry, because phi, right? Phi is what is known as the phi component is what is known as azimuthal. Okay, symmetry means that should be 0. Okay, that is the meaning of symmetry. You know from classical mechanics, right? Some term should be absent. Either you say absent or you say 0. So if this particular quantity is absent, the absent means what? Delete. If you delete, what will happen? You get this. So that is what I am trying to say. Okay, azimuthal symmetry is, that is what it is. Okay, symmetry means something is going to be 0, or you can say something is absent. If that happens, then what will happen to the associated Legendre differential equation, ALD? It will become a simple Legendre differential equation. So the extra term that we have added is going to tell you whether the symmetry is present or absent. If the symmetry is present, it is 0. If the symmetry is absent, not equal to 0. Therefore, these things are directly connected to the spherical polar coordinate system. And the radial component, I already wrote you the Cauchy Euler equation. You also see the solution. Okay, so these are the basic things that are required. Once you understand things, then it is easy to grasp what is going on next. So these things are, of course, now you have you're able to understand how the how the information that we studied in today's class, starting from the sin theta graph. Sin theta graph is corresponding to this phi variable, and you see that is the one which has the m. So now you should be able to again go back to the in the beginning of today's lecture. The beginning of the today's lecture was a sine of theta, right, or sine of phi, and we have said that sine of m phi and m equal to 1.1, 1.2. That m is this m. Now you understand that m is coming here. So that number, what we are going to substitute is any number can you put, or an integer you can put. That was the question, and now you can now understand that m is going to belong to an integer only. So why, on what basis we write m belongs to integer should be clear. Okay, just because it is printed in a textbook, you also cannot copy it here. So that is why in the very beginning I explained that when we are going to have 0 to 2 pi as the range for this azimuthal angle, over that angle 0 to 2 pi I need a periodic function. If it is non-periodic function, then what is the problem means? What's the problem? The function will not be periodic means if I make one round and come to the original place, I will have a different value. Periodic function means it will repeat itself. The value at 0 and the value at 360 degree are identically same. So I can go n number of time. I can go 100 times and then come and stand in the original place. I will have the original value with me. But if you have a non-periodic function, the non-periodic function means what? You make one round and come back to the original place, I will get a different value. Again you go another one round, 2 pi, another 360 degree and come back to the original place, I will get another value. That is called a non-periodic function. So that is not meaningful, right? We don't have such kind of solution. You are actually coming back to your original place, and how can you say that electric potential is now different just because you traveled 360 degree? It is meaningless. Therefore, because of this kind of meaningful discussion that we want in a situation, mathematically we demand that these kind of numbers like integers only work. Okay, and it happens to be a positive value here. So we are always emphasizing that this is a positive value. This minus is taken care for other reasons. So now that you now today we are able to see that somehow these differential equations are directly connected to the spherical polar coordinate system r theta phi. But then now you may get a doubt. Then what is this x coming into picture? Okay, spherical polar coordinate system means r theta phi, that I agree. Then why x should be there and y should be there? X and y is generally Cartesian coordinate, right? So why you have Cartesian coordinate here? So that confusion may be there. I would like to emphasize that this kind of y and x is written for traditional mathematical introduction. Okay, whenever a particular equation is introduced first time, we say y equal to f of x. Okay, that is this y. F of x is the entire function, whatever function that you have. So it is just for introducing a particular function in terms of x. People simply write in terms of x, but originally it is not at all x. It is related to these three variables, and therefore I would like to address this issue or this particular point, how this expression is entirely related to the spherical polar coordinate system, and there is no question of x coming into picture. We don't have x coming into picture. Dependent variable, not a problem. You give any name, that's okay. Okay, independent variable has to be r theta phi. These three are the independent variable. Dependent variable name anything you can give, f of x, g of x, whatever it is. So that is not a problem. So let us therefore see in the next class, in the case of the spherical polar coordinate system, how this x has to be eliminated and bring the original variable r theta phi. Okay, that part let us see in the next class.